Okay, so I always like to start the polynomials topic from a place that we already know. So that is looking at the extended versions of the quadratic function. So looking at, we know about x squared and how to transform it. Okay, so then we also know about, if we know what y equals x cubed looks like, we can also transform it. If we know what y equals x to the power 4 looks like, we can also transform it. And actually we could draw any polynomial graph in turning point form, regardless of whether it had a power of 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Let's take a step back, because I did mention in the previous video that our polynomial graphs, the larger the power, the more variety that can happen. Let's also take a step back as to what actually makes a function a polynomial function. So a quadratic is a type of polynomial function, as is a linear function. We've looked at the two most simple polynomial functions already: linear functions, quadratic functions. Now we've moved on to cubic functions, quartic functions, and they extend to, after that, we just call them degree 5, 6, 7, 8, etc. polynomial functions. So a polynomial function has this kind of form. It's a really unnecessarily complicated way of describing it, but essentially we have a number times x to the power of n plus another number times x to the power of 1 minus n plus another number times x to the power of 2 minus n, all the way down to we get a constant term, that is e to the power of e times x to the power of 0. So our decreasing powers of x, and we can have coefficients of each of those terms. Now some of those could be missing. For example, if b was 0, we wouldn't have this term. For example, we go straight from, let's say this is, 2x to the 7, maybe it's 0x to the 6, so we don't really have that term there, plus 1x to the 5 minus x to the 4, maybe we've got a 0x cubed, so we don't have an x cubed term, whatever it might be, okay? But these would be examples of polynomials. So each term in the polynomial is a power of x, possibly with a coefficient, and they're added together. Obviously, when we have polynomial functions, we're familiar with quadratics. They can be written in different forms. It's possible to factorize polynomial functions. We'll look at that in some depth. So they can be written in various kinds of forms. And as we saw in the previous video, sometimes, if it was a degree 7, it might be able to be written in this kind of form. And in that case, then it would be a sort of more extreme cubic shape transformed to the right by h and up by k. Okay. But what we want to look at is, start to think about, is some of the other things that can also happen with polynomials. So the highest power of x is called the degree of the polynomial. So in a quadratic, that's a second degree polynomial. In a cubic, that's a degree 3 polynomial. Quartic is a degree 4 polynomial. As I said, after degree 4, we run out of special names and we just call them degree 5, degree 6, etc. So the lowest degree polynomial is the linear function. It's degree 1, ax to the power of 1 plus b. Okay, every linear graph is going to look something like this. Okay, it might be reflected and sloped down. It might, we can have linear graphs that are horizontal and vertical as well. They're slightly different cases. But the most basic linear graph is going to look something like that. Then we have a degree 2 polynomial, which we're also familiar with. It's a quadratic function. The highest power of x is 2. That's what makes it degree 2. And all quadratics form a shape called a parabola. Again, they might be reflected, but the shape, every single quadratic is going to be a parabola. Then we increase the degree to degree 3, and we now have a cubic function. The highest power of x is 2. It could have up to 4 terms. As I said, if b was 0, it would only have 3 terms. If d was 0, it could only have 3 terms. It could have no c or d. That would still be a cubic. As long it could have none of these terms at all. That would still be a cubic. So as long as the highest power of x is 3, it's a cubic function. It can have up to 4 terms when it's expanded out. And a cubic function is going to look something like this. Now, as we saw in the previous video, it can also look like this. And that is if the equation can be written in this form. Then it would look like that. Okay? But most cubics are going to look something like this instead. Okay? Now, perhaps most isn't it extreme, is perhaps not always true, but a lot of cubics. Then a quartic function is degree 4. Highest power of x is 4. It could have up to 5 terms in its expanded out form. And it can have up to 3 turning points. It could look like this. Okay. As we talked about in the previous video, there are other variations of what could happen. 2 of those turning points could kind of be combined into a point of inflection. Okay. In that way, or those 2. So it would go this way. Similarly, all 3 could be combined together in that sort of flat-bottomed quartic shape, and we could get this sort of thing. And there are also other things, because the points of inflection don't have to be stationary, so it could just be a light bend rather than a stationary point of inflection. There's actually a lot more variety of what could happen. As I said, the higher the degree, the more variety there is. We're really only going to be focusing on these shapes for the quartic, these shapes for the cubic. Obviously, they can be reflected, so they can go up the other way, but these are the basic shapes, and we'll build up our skills to be able to work with those throughout the topic. If we had a degree 5 polynomial, it could have up to 6 terms. Its leading term, so the leading term is usually the highest power of x, would be ax to the power of 5, plus bx to the power of 4, plus cx to the power of 3, plus dx squared, plus ex, plus f. Okay. And if we think about what's happening here, as I said, there's a lot of variety that can happen, but a linear graph has no turning points. A quadratic graph has 1 turning point. A cubic graph can have up to 2 turning points. A quartic graph can have up to 3 turning points. A degree 5 polynomial can have up to 4 turning points. Okay, again, there are things that can happen. 2 turning points can combine together to a point of inflection, and you get something like that instead. And all sorts of other things. You could have 2 points of inflection. That one's not right, sorry. Because it won't turn as well. Anyway, but there's lots of different things. You could have 2 points of inflection that would go this way. That would also potentially be degree 5. So there's a lot bigger variety of what can happen, but up to 4 turning points. So degree 1 polynomial, no turning points. Degree 2 polynomial, 1 turning point. Degree 3 polynomial, up to 2 turning points. Degree 4 polynomial, up to 3 turning points. Degree 5 polynomial, up to 4 turning points. Okay. As we've seen with quadratics, polynomials could also be written in a factorized form, and we need to learn how to factorize polynomials because it's a really key skill for us sketching their graphs. We'll build up the skills to be able to do that. Or they might be able to be written in this form, but not all polynomials other than quadratic. Every quadratic can be written in this turning point form, but not all cubics, quartics, degree 5, etc. polynomials can be written in that form. If they can be written in that form, then they're going to be these sort of shape. Okay, that for odd degree, that for even degree. If not, be one of these other kinds of shapes. Okay, in any polynomial, the term that's independent of x is called the constant term. Okay, so that's and when we talk about that, that is in this expanded out form. So b is the constant term here, c is the constant term here, d is the constant term here, f is the constant term here. Please note that k is not the constant term here, because when you expand out this bracket, there'll also be a constant come in there, and that'll be combined together with k to produce the constant term. Again, d is not the constant term. It's not just the number on the end. If we were to expand out all these brackets, we would have a number on the end that's a, b, c, d. Okay, that would be the constant term. So you need to think about what the function would look like in its expanded out form. As I mentioned, the leading term is the term with the highest power of x, and we usually write it first. Coefficients are so the coefficient of x to the power of 4 in this polynomial would be b. Okay, so just being confident with that language we use around polynomials. So let's have a look at an example here. Consider the following polynomial functions. What is the degree, and state the constant term. Okay, so in f of x, that's a degree 1 polynomial. The highest degree is 1. Okay, and the constant term there, that is the term that is independent of x, is 3. Okay, in g of x here, the degree, highest power of x, is 3. And the constant term, the term independent of x, is negative 7. H of x, okay, so this is not expanded out, but we should be able to kind of think through the answers to this question without needing to fully expand out the function, okay? So if we were to think about the degree of this polynomial, if we think about expanding this out, the highest power of x is going to come when we do x times x squared. So x cubed is going to be the highest power of x. I don't need to work out all the other terms, I'm just interested in the constant term on the end, and that's going to come from when I do my expansion, when I do negative 3 times positive 4, so negative 12 will be my constant term. They're the two things I'm interested in to answer this question. So the degree is 3 and the constant term is negative 12. Alright, k of x, highest power of x there is actually, it's out of order, so just be careful about that. Highest power of x is 4, so it's a degree 4 polynomial. And the constant term, again, it's out of order, so be careful. It's not the number on the end, it's the term that's independent of x. So it's this one here. Plus 5, positive 5 is the constant term. m of x, again, it's not expanded out, so let's be careful. 4 is not the constant term here because there's going to be a constant that comes out of that bracket. So if you think about this, when you expand out that x minus 1 all cubed, again, I'm not really interested in all of it, but it'll have x cubed at the beginning, and it'll have -1 times -1 times -1, so -1 at the end, okay? And there'll be plus 4. And then it's 2 times all of that bracket, so it's 2x cubed minus 2 plus 4. And so those things together will come together to give us our constant term here. So it'll be plus 2. All right, so part 1, the degree is a cubic, and part 2, the constant term is positive 2. Okay, n of x, we see there that the highest power of x is 7, so it's a degree 7 polynomial. Oops, sorry, not part 3, part 2. And the constant term is the term independent of x. There isn't a constant term. That's because the constant term in this case is 0. Alright, p of x, again, not expanded out. So let's think about what would happen if we expanded it out. The highest power of x is going to come from when we do x times x times x. So it's going to be cubic. And then if we were to expand out, so actually, let's just do a step before that. If I were to just think about expanding out these two brackets, okay, we could do it all, but I'm really only interested in the first and the last term. X squared, and then it'd be 1 times -4, so it'd be -4 at the end there. Then when I expand out this polynomial, I'm going to have x cubed at the start and minus 4x at the end. So actually, the constant term here is going to be 0. So the degree of this polynomial is cubic. The constant term here is 0. Alright, q of x. Again, let's think about what would happen if we expanded it. So the highest power of x is going to come from when we multiply the two highest powers of x in each of the brackets together. So x squared times x squared. Sorry, I don't need a bracket there. It's going to be x to the power of 4. And then I'm not really interested in all the terms in the middle. The constant term is going to come from when I multiply the constant term in the first bracket by the constant term in the second bracket. So that will be -5. So my degree here is degree 4, and my constant term here is -5. And then finally, r of x is a quadratic function. If you think about expanding that out, you're going to have x squared plus 4x plus 4 with the perfect square. And so the first term is going to be half x squared, and then you're going to have half times 4, which is plus 2, and then take away 3. So you're going to have half x squared and minus 1 at the end. So your degree is 2, and your constant term is -1. Okay, example 2. Consider the following polynomials. So we've got 3 polynomials here. F of x, which is a degree 1 or linear polynomial. G of x, which is a degree 2 or quadratic polynomial. And h of x, which is a degree 3 or cubic polynomial. So if we want to work out f of 10/9, so again, some practice of our function notation. F of 10/9, so we're replacing x in function f with 10/9. So f of 10/9 means instead of having 3 times x minus 1, we're going to have 3 times 10/9 minus 1. 3 times 10/9, yes, I can write it as 30 over 9, but it's easier to think about cancelling the 3 down with the 9. So it becomes 10 on 3 minus 1. 1 is 3 on 3. 10 on 3 minus 3 on 3 is 7 on 3. Alright, g of 2/3 means we're replacing x with 2/3 in g of x. Okay, so instead of having x squared minus 5x plus 6, we have 2/3. Sorry. We have 2/3 squared minus 5 times 2/3 plus 6. 2/3 squared is 4/9. 5 times 2/3 is 10/3 plus 6. We're going to need a common denominator to add those together. Common denominator is 9. So it's 4/9 minus 30/9 plus 54/9. Okay. Now again, you can think about order here. You might add the 4 and the 54 to get 58, and then take away the 30 to get 38 on 9. You might take the 30 away from the 54 first to get 24, and then add 4 onto, oh sorry, I've done that wrong, haven't I? 28. And then add 4 onto it. So you don't have to do 4 take away 30 is -26 and then work out what -26 plus 54 is. That flexibility with your arithmetic is going to enable you to be more efficient, okay? So those things can happen in any order. It's easier personally for me to think about either doing 54 take away 30 is 24 plus 4, which is 28, or to maybe think about 4 plus 54 is 58, and then take away 30, which is 28. Making sure your fraction's in simplest form, but there's no common factors between 28 and 9, so that's done. H of negative 2. So H of negative 2 means we're going to replace the x in H of x with negative 2. So wherever there's an x, it's going to become a negative 2. So we're going to have 5 minus negative 2 plus 7 times negative 2 squared plus negative 2 cubed. Okay, so it's 5 minus minus 2, so it's 5 plus 2. Negative 2 squared is positive 4, 7 times 4 is 28. Negative 2 all cubed is negative 8. Again, some flexibility here. 5 plus 2 is 7, 28 minus 8 is 20, so 27. F of x plus g of x. Okay, so f of x is 3x minus 1, and g of x is x squared minus 5x plus 6. So that's f there, that's g there, and we're adding them together, so we can just collect some like terms. X squared, we've got 3x minus 5x, that's minus 2x, negative 1 plus 6 is plus 5. 4 times h of x. Okay, so we're going to have 4 times h. Now let's just copy h down from up here. H is 5 minus x plus 7x squared. Oops. 5 minus x plus 7x squared plus x cubed. I'm going to do 4 times that. So that's going to be 20 minus 4x plus 28x squared plus 4x cubed. So we're just looking at working with the arithmetic of polynomial functions. Alright, f is 3 times f of x minus g of x. Okay, so we need 3 times f of x. Now f of x is 3x minus 1. Take away g of x. Now, careful because you're subtracting. Make sure you put g of x in a bracket because you're going to need to subtract everything. So g of x is x squared minus 5x plus 6. Okay, so 3 times f of x is 9x minus 3, and then we're taking away x squared, but we're adding 5x, and we're taking away 6. Let's collect those like terms together. Let's write it in decreasing degrees. Decreasing powers of x. So we've got negative x squared is the highest power of x, 9x plus 5x, so 14x, and negative 3 minus 6 is negative 9. Alright, if we do f of x times g of x, so f of x is our linear function, 3x minus 1, g of x is our quadratic function, x squared minus 5x plus 6, and so multiplying those together, let's just multiply everything by 3x, so that gives us 3x squared minus 3x cubed minus 15x squared plus 18x minus x squared plus 5x minus 6. Collecting like terms, 3x squared, we've got minus 3x cubed minus 16x squared, and then plus 23x and minus 6. So just having a look at sort of what we're doing here, when we add together two polynomials, if we add a linear and a quadratic together, we still get a quadratic. Adding them together doesn't sort of increase the degree of them because you're just collecting like terms, you're not multiplying any terms together. Multiplying a function by a constant value is not going to change its degree. H of x was a cubic, 4 times h of x is still a cubic. Subtracting two functions. In this case, we were subtracting a linear minus a quadratic. We still end up with a quadratic. So again, we're not multiplying any terms together, so we're not increasing any of the powers. So it's still going to just be the highest power of x. Whereas h of x, when we multiply a linear times a quadratic, we end up with a cubic. Okay. If you were to think about it, if we were to do the linear times the cubic, we would have a degree 4. If we were to do the quadratic times the cubic, we'd have a degree 5. Okay, so multiplying them together is going to change the degree. Similarly, dividing would as well. We'll have a look at the division of polynomials in the next video. It's a more complicated process that it requires some new skills. Okay, so following on from that, then example 3 is trying to generalize some of the things we looked at in the last example. If p of x is a polynomial of degree m, and q of x is a polynomial of degree n, and m is bigger than n, so that means p is a higher degree polynomial than q, then what is the degree of p plus q, so if we were to add together these two polynomials. So we saw when we added together two polynomials up here in D and F, add or subtract, we don't change the degree. The resulting answer is obviously just going to still have the highest degree that we started with. So here p is the higher degree polynomial, it has degree m, and so p of x plus q of x will be degree m. Okay, if we do a degree m plus a degree n, where m is bigger than n, then m will be the highest power. If we do negative 2 times p of x, so again we saw up here in this previous example in part E, when we do a constant times a polynomial, it doesn't change its degree, so p of x has degree m, and so therefore negative 2 times p of x will still have degree m. Multiplying by negative 2 is only going to change the coefficients, not going to change any powers. If we did p of x times q of x, so this would be a degree m polynomial times by a degree n polynomial. So the highest power is going to come from when we multiply those two terms together, and index laws tell us when we multiply x to the m times x to the n, we get x to the m plus n. So this will be a degree m plus n polynomial. So we saw that here when we did degree 1 times degree 2, we ended up with degree 1 plus 2 of 3. Okay, a couple more examples. Find the value of c if p of x is equal to this polynomial, so there's c there, it's a part of an unknown coefficient, and p of 1 equals 21. Okay, so this is simply giving us a point on the graph. It tells us when x equals 1, the polynomial is equal to 21. And so we can just substitute that in. So p of 1 means getting 2 times 1 to the power of 4 minus 1 cubed plus 2c times 1 plus 6, and we know that has to equal 21. So we can solve this equation for c. 1 to the power of 4 is just 1, so this is 2 times 1 minus 1 plus 2c plus 6 equals 21. Alright, 2c, 2 minus 1 is 1, and plus 6 is 7. If we take away 7, we get 2c equals 14, and divide both sides by 2, we get c equals 7. And then finally, example 5, the polynomial p of x, which is that cubic there, can be written in the form p of x equals x minus 2 times x squared plus bx plus c plus r, where b, c, and r are real numbers. Find the values of b, c, and r. Now down the track it would be possible to use polynomial division for this process to work out, to divide our polynomial by x minus 2, but actually in some cases a more efficient method might be to do what we're going to do now. So what we know is we know that this is equal to this. They are the same thing, okay? So we know that x cubed plus 3x squared plus 2x plus 1 is equal to x minus 2, x squared plus bx plus c, and then plus r. Now, we know that if two polynomials are equal, they have to have the same degree, and these are definitely both cubics, and all of the each of the coefficients of each of the x squared, x cubed, x, and the constant term, they all have to be equal as well. So if we can expand this out to get it in this same form as this, we can see, okay, we know the number in front of x cubed has to be 1. We know the thing in front of x squared has to be 3. We know the thing in front of x has to be 2, and we know that the constant value has to be 1. So that's our goal. So let's expand out the right-hand side so we've got the two things in the same form, and then we can do what we call equating the coefficients. So if I expand out these brackets, x times x squared is x cubed. We're going to have plus bx squared plus cx, and then we have minus 2x squared minus 2bx minus 2c, and then plus r. So we just need to collect some like terms together. So we've got x cubed. Now the x squared terms are bx squared minus 2x squared. So if we factor out the x squared, we've got b minus 2 times x squared. The x terms, we've got cx minus 2bx. So therefore it's, if we factor out the x, it's c minus 2b times x. And then the constant terms, we've got plus r minus 2c. So we've just got those two values there at the end. Okay, so now we can equate the coefficients. We know that we're going to have 1x cubed and 1x cubed. We know that we're going to have positive 3x squared, so that has to equal positive 3. We know we have positive 2x, so that has to equal positive 2. And then we know, just let me get another highlighter colour, we know that the constant value is positive 1. Okay, so obviously we learn nothing from equating the coefficients of x cubed. If we equate the coefficients of x squared, we learn that b minus 2 has to be equal to 3, and so therefore b has to be equal to 5. If we then equate the coefficients of x, we learn that c minus 2b has to equal 2, and we know what b is now, so that c minus 10 has to equal 2, and so c has to equal 12. Okay, so we just subbed b in there. And then we know that equating the constant terms, that r minus 2c is equal to 1. Again, we know what c is, so that's r minus 2 times 12, which is 24, equals 1, and so r has to equal 25. And so we get the values of b, c, and r. Make sure we answer the question. If it asked us to write down p in this form, we would sub them all back in, but it just says to find b, c, and r. B is that, C is that, R is that. We've answered the question. Okay, so there's a variety of just arithmetic with polynomials, adding, multiplying by a number, multiplying polynomials together, and also just some practice with sort of function notation to just get you a bit warmed up here in exercise 6A.